All right, welcome everyone. Welcome everyone to the first talk in the TUT's 100th Distinguished Lecture Series. Every week of this term, we're going to be hosting a distinguished invited speaker that works at the top of one of the department's research areas to give the TUT colloquium. We have a really exciting list of names lined up, as well as today's speaker. If you're interested to see who we can look forward to, there's some information here and posters in different parts of the department and also on the CNO website. Today, it's my great honor to introduce our first speaker, Dr. Gerard Cornuejols. Dr. Cornuejols has his PhD from Cornell and is the IBM Professor of Operations Research at Carnegie Mellon University. His work across optimization and operations research is well known. He is the recipient of the George B. Dantzig Prize, the Fulkerson Prize, and the John von Neumann Theory Prize, among others. He's the author of 3 textbooks. Today, Dr. Cornuejols will be telling us about optimality certificates for convex minimization and Helly numbers. Thank you.
Thank you very much. It's a great honor to give a lecture in this series. And I thought I should give a really kind of a big lecture. But in the end, I'm going to present a small result. I think it's cute. Might even be might be even useful, although we've not managed to make it useful yet. But that was the intent when we started. I was visiting ETH Zurich, where Robert Weismantel and Stefan Weltge work, and at the same time also Amitabh Basu and Michele Conforti were visiting, and so we kind of teamed up and started thinking about the following problem. So the problem is very simple to state. You have a convex function from Rn to R, and you have a very general set of feasible solutions S, and you just want to find the infimum of F over the points in S. So just to try to fix ideas a little bit here in R2, we have this convex function. I kind of drew some level curves where, let's say, the minimum here is in the middle, and then you have the line where the function f is equal to 1, equal to 2, and so forth. So you have this convex function, and we have some set of feasible solutions S. Let's say it's the lattice points, the integer points in R2. And we would like to find the infimum of the function over this set S. So typically we'll think of S as kind of some discrete set, so that's basically, that was the motivation that we had. But we were just at this point making it kind of very general. And so if you look here, you can see that there is actually a point with value 3, and then here there are a couple of points with value 4. So if you want to find the minimum, here you'd find that the minimum value is 3. Okay, and what we would like to do is we would like to somehow have a certificate that this is indeed the optimum solution. So how do we come up with some certificate that can prove that this is indeed the optimum solution? So that's the goal. We would like to describe some geometric dual, some object that's kind of basically allows us to certify that we have an optimum solution. So it's basically, it's kind of in the spirit of duality. And of course, any of you who's done a little bit of optimization knows how fundamental duality is to optimization, linear programming duality, and the work of Jack Edmonds in combinatorial optimization, and primal dual algorithms. And if you talk about continuous optimization, interior point algorithms, this is all duality is very central to any of these, and so that was actually our goal was to say, okay, let's try to come up with some primal dual algorithm for this problem, and we were not able to do that, but the first step is really to come up with this kind of certificates. How do you come up with a dual certificate that will prove optimality? So I should say that for linear integer optimization, there's been some work dating back to the 1970s. Dating back to the work of Gerard's law and Bob Gerard's law, Ellis Johnson, Charlie Blair, Lawrence Woolsey. There was quite a bit of activity in the 1970s in this area. That's for linear integer optimization. But for nonlinear integer optimization, actually, there is not all that much that's been written. There's been some nice work recently, Morandi and Vielma, for conic mixed integer problems, where you just have a kind of a very special kind of convex problem. It's a conic optimization problem, or Bayes, Ortel, and Weismantel for general convex mixed integer problems. And that's basically kind of the spirit that we're going to continue thinking about today. So some very general kind of duality. So so again, the problem that I'm looking at is trying to find the infimum of f over points in some feasible set S. And let's make a couple of assumptions to kind of simplify things a bit. I'm going to assume that the infimum of the function over Rn is actually attained. And let's x0 be a point where the infimum is attained. So we're going to assume that actually the minimum exists. And then we're going to say that a closed set C is an S-free neighborhood of x0 if x0 is in the interior of this convex set and there is no point of S in the interior. So you may have points of S on the boundary of this convex set C, but not in the interior. So that's what we call an S-free neighborhood of x0. And it is not hard to see that if I have an S-free neighborhood of x0, then if I look at the boundary of that convex set and I take the infimum of f over that boundary, that is going to be a lower bound on any solution for for any feasible solution. And it's kind of a weak duality type of result. And it's pretty easy to see. It just follows from the convexity of F, right? I mean, you just have this point x0. In the interior, you have your point S bar, which is outside. And so, you just look at the line segment between S bar and x0. At some point, you're going to cross the boundary. And obviously, you're going to have that f of S bar is greater than this value at the boundary. And now, of course, if I take the infimum over all points on the boundary, I get my lower bound, right? So, so that gives us some direction to come up with kind of some dual. So basically, that's what I'm repeating here. An S-free neighborhood of x0 can be interpreted as a dual object that provides a lower bound on our primal problem. And of course, if I can find an S bar in my feasible set and a convex set C, which is an S-free neighborhood of x0, such that I have equality here, then, of course, I have a proof that S bar is an optimum solution. Yeah. OK, so let's use that to kind of guide us towards this dual. So if I have an S-free neighborhood of x0, C, let me denote by L of C the infimum of the function value on the boundary of C. And now, if I have a family of kind of script F of S-free neighborhoods of x0, then I can define an F dual as being the sup over all the convex sets in that family of this L of C, right? So I'm going to assume that when I minimize my function f of x, the minimum is not a point in S already, because then my problem is solved. I mean, if I just minimize my function f and I get a point in S, then I'm done. And so, I know, a certificate would just simply be a zero subgradient at that point, and that's it. So let's assume that, in fact, S is disjoint from the set of continuous optimum solution. So when X is in Rn. Then it's not very difficult to see that if I pick my family script F as the family of all S-free neighborhoods of x0, then strong duality holds. In other words, I have my primal problem. The infimum here is going to be equal to the value of the dual. Why? Well, I said that I'm assuming that the minimum is achieved, and you could just take the value of that minimum and then look at your set C to be the convex set where the function value is less than or equal to that value. So, and then you're going to match this optimum solution with this dual. So yes, so we know how to construct a dual, but of course the problem is that if I take all, if I look at all S-free neighborhoods of x0, that's really just too general. I mean, there's not much structure there. So the entire family of S-free neighborhoods is just too unstructured to be useful. And so the goal is to try to restrict our family script F and try to see when we still have strong duality. That's what we really want to do. Well, let's notice that, one of the easy things that we could do is just to look at a maximal convex S3 neighborhoods of X0, maximal in the set sense. So in the sense that set is maximal if it's not strictly contained in a larger convex S3 neighborhood. And for certain classes of feasible sets, of sets S, such as the integer lattice, the integral lattice, or this mixed lattice, actually, this family is actually pretty nice in the sense that it only contains polyhedra. And that is already a very nice, there's a very nice property. There are two reasons why polyhedra are particularly nice. One is that they are easier to represent and to compute with. And in fact, if you look at this problem that we have to solve in the dual, that is, we have to find the minimum on the boundary, then because we just have a finite number of facets for polyhedra, we can just look at each facet separately, and what we have to solve then is a continuous convex optimization on each of these kind of facets. So the optimization problem for computing L of C becomes more tractable. Okay, but we want to restrict this family further. And so an idea is, okay, can we kind of relate this polyhedra to the function f? And so we're going to define a gradient polyhedron as follows. For a finite set of points, z1, zk, we're going to take a gradient at point zi, or if the function is not smooth, a subgradient. So let ai be a subgradient of the function f at zi. And then let's just look at the half space. So from zi, we have this subgradient direction. We just look at the half space where the inner product ai x minus zi is less than or equal to 0. And then we intersect those k half spaces to get our polyhedron. Okay, so if the polyhedron is defined this way from these subgradients, we're going to call it gradient polyhedron. So just to illustrate in my little example here, let's assume that I have a finite set of 5 points, z1, z2, z3, z4, z5 are my 5 points. And then here the function is smooth, so I just take the gradient. And that's going to define one boundary line of my polyhedron. And similarly at z2, similarly at z3, z4, z5. And now I have here my gradient polyhedron. And the nice thing here is you may notice that actually, the minimum in each of these facets is going to be achieved at zi, right? So I really only have to, if I want to find the minimum on this boundary, I just need to take the minimum of these 5 values, Z1, Z2, Z3, Z4, Z5. So this is this idea was actually proposed by Bass, Ortel, and Weismantel in the context of mixed integer programming, where their set S is some mixed integer set in where just they take the points in some convex set gamma, kind of some of the variables are restricted to be integer. And they showed that if you take the family of convex S3 neighborhoods that are gradient polyhedra for some finite set of points, this actually enjoys strong duality. So you have strong duality in this case, okay? Now, here, they picked any point from Rn. It'd be nice if we could actually pick points from S. So that's really what we wanted to do. That's what I'm going to talk about today. So let's define the same thing, denote this way the family of convex S3 neighborhoods that are gradient polyhedra for some finite set of points in S. Right? We only want to pick points in S where we take this subgradients. And we're going to investigate when we still have strong duality in this case. And we would be interested in really picking the maximal sets in that. So so let's just basically redefine from scratch. We can forget about earlier definitions, and let's work with this definition. So we're going to say that we have a strong optimality certificate of size k if we have a set of k points, z1, zk in S, together with subgradients of the function f at zi, such that q is the subgradient polyhedron at these k points. I'm going to impose that q is S3, and I'm also going to impose this additional condition. It's not clear how feasible it is to impose it, but if we can impose it, it would be nice. What I want is that for all I different from j, actually I'm going to have strict inequality here. In other words, on the facet corresponding to zi, there's only the point zi on that facet. I don't have any other zj on that same facet. So here's an example where I have 4 points, z1, z2, z3, z4, and this quadrilateral, so I'm just taking the gradients here at those 4 points, and so this is S3, and it has these properties. It's S3, and it also has this nice property that each of these points here is actually interior to the corresponding facet, and there's nobody else. There is no other point in my set z1, zk that's on that facet. In other words, there's kind of some one-to-one correspondence, nice correspondence between the points and the facets. So now, of course, this all sounds good, but so here I kept the definition of a strong optimality certificate. And let me just make a couple of remarks. First, because A is a subgradient, for every point x in Rn, I'm going to have f of x greater or equal to f of z plus this inner product. Because in the end, I have a set Q which is S free. For every point in S, there must be some Zi such that I have inequality. This inequality holds for at least one I. And so what that shows that f of s is greater or equal to f of zi for at least one I. And so now if I take the minimum of fzi over this k values, then clearly f of s is always greater or equal to this. So that's kind of nice because then what I have is that, if I give you a strong optimality certificate, then to compute the solution of the primal problem, the only thing that you have to compute are these k values and take the smallest, and that's going to be your optimum solution. So if a strong optimality certificate exists, actually it even also implies that the infimum of f has to be attained because really this infimum is actually just the minimum of a finite number of values that I can compute explicitly. So this all looks very nice. Of course, there's a catch, and that is, I didn't tell you how to compute, how to find a strong optimality certificate. And I just want to say a couple of words on this. It's still not, it's not going to be an easy problem in general. Of course, we all know that this optimization problem is difficult. So if we could find easily this optimality certificate and then just pick the smallest value of the FIs, of the f of zi's, that would be too easy, right? But okay, so what do we have to do if we have k points and k subgradients? I'd like to verify that this gives me a strong optimality certificate. Well, the main thing that I need to check is whether the polyhedron that's defined this way is S-free. And that's actually not an easy task in general, just for finding whether a polyhedron contains an integer point. That's a difficult question. So that's what I wrote here. Deciding whether a general polyhedron is S-free is a difficult task. However, turns out that the second property that I required here actually implies that this polyhedron Q is actually maximal. And it's actually not that difficult to show that Q is maximal because, if it were not, then some facet of Q would actually have to, at least one of the facets would have the interior, the relative interior of one of the facets would have to be contained in this larger set. And therefore, our point Zi, which is in the interior, would actually become interior to this larger set. So actually, so this Q is actually maximal S-free, which is nice because the properties of maximal S-free sets is well understood for certain kinds of sets S. For example, going back to the situation where S is in some closed convex set gamma, and there's kind of some mixed set inside it. Actually, it's been shown that such maximal S3 sets are polyhedra with, at most, this many facets. Of course, that's still not a lot of structure. But if you go back to the plane, if you go down to the plane, then this is a situation where the maximal lattice-free sets are really well understood, and we can actually there is a very simple algorithm to detect whether a polyhedron is maximal in that case. It is helpful to be in the context of maximal S3 sets. Okay, so to state the theorem, let me first introduce the notion of Helly number of a set S. The Helly number of S is the largest number of convex sets. Let's denote them C1 through Cm. The largest M, such that if I intersect all these convex sets, I intersect all these CIs, there is no point in S in the intersection. But if I intersect all but one of these sets, so for every J, I'm going to remove one of the sets, then now I have a point in S, right? So I'm just to give an example, let's say that you are looking at the vertices of a square. So the S is just 4 points, the 4 corners of a square. And let's construct sets C1 through C4 that essentially are the convex hull of 3 of the 4 points. So I get 4 triangles. And now if I intersect those 4 triangles, then I'm going to get, well, I guess just the center of the square. But that's not in S, because the S only contains the corner. So the intersection here is empty for those 4 sets, those 4 triangles. But now if I intersect only 3 of the triangles, it's going to contain one of the vertices of the square, right? So that shows that the Helly number is at least 4. And in fact, it is 4. It is 4. In fact, it's 4 even for the whole integer lattice and the plane. OK, so we have this notion of Helly number. And the theorem says that if I have a convex function f, and this set S of feasible points, and I make like 3 fairly mild assumptions, maybe not so mild, but fairly mild assumptions. Under these assumptions, I can conclude that there exists a strong optimality certificate of size at most the Helly number of S. Right? That's the main theorem. And and maybe I can discuss a little bit those 3 assumptions. So actually, so I repeated the theorem here. And and let's look at the first assumption. So my first assumption is that there is no point in S where I have a 0 subgradient. And we said, well, if that's the case, then the problem is really easy. So I really want to exclude this trivial case, basically. So so if I have a 0 subgradient at S star, then S star is an optimal solution, and we're done. And I also have a nice certificate, which is just this 0 subgradient. So I'm going to assume that I'm not in that trivial case. I'm also going to assume that the Helly number is finite. And okay, and yeah, here I have some comments about this. So the characterization of closed sets S for which the Helly number is finite, has actually received attention. There's a nice paper by Averkov. And for example, this case that I've already mentioned a couple of times, when S is of this mixed integer set, then the Helly number is finite, and in fact, there is an explicit bound on the Helly number. Okay, and then let me talk a little bit about this third assumption. So I'm also assuming that for every polyhedron P, which contains a point of S in its interior, there's actually a point of S in the interior that actually achieves the infimum. So I have a minimum in this case. So I'm assuming that for every polyhedron, I have this property. In particular, if I have all of Rn, I'm saying that actually the infimum is achieved, right? So that's one of the assumptions that we make. And just to give you a couple of examples, there are many situations where this holds. But as an example, if S is a discrete set, like for example the integer lattice, and if F is strictly convex and has a minimizer, then I have this property. And irrespective of the function F, if S is a finite set, I automatically have this property. It's easy to see. So for example, we are interested in the integer points in some compact convex set, then we can we satisfy this, and so we're going to have a strong duality certificate. Yeah, let me show that. Assumptions 1 and 2 are pretty, I guess, non-problematic. What about assumption 3? Well, actually, we really need assumption 3 because here's a little example where, if I do not have 3, and I do not have 3 in this case, my set S is defined this way. Square root of 2x1 minus x2 greater or equal to 0, and then some non-negativity conditions on x1 and x2. And if my function f is this, and I'm trying to minimize, it's easy to see that in fact the infimum is 0 and it's not achieved. So I cannot have an optimality, a strong optimality certificate in this case. Okay, so let's see. I probably have enough time to give you a little idea about the proof of the theorem. So we rely on this little lemma here. So I have a polyhedron P, and I'm interested in the vertices of P. In fact, I'm interested in the situation where where I have a set V such that if I take the convex solve of these points, the vertices of that polytope is my set V, right? So I'm only looking at, I have a polytope, and I'm only looking at the vertices of that polytope, basically. And what I'm saying is that if it turns out that all these vertices are in S, and I don't have any other point in S in the convex hull of V. So in other words, the intersection of the convex hull of V and S is just V itself, right? Then I'm going to have the property that the Helly number of S is at least cardinality of V. And that's actually very easy to see. That's not a deep result at all, but that's the basis of why this strong duality certificate holds. So let's try to see where this lemma comes from. So let V be denoted V1 through Vm. And now let's look at the convex set Ci, which is the convex hull of V minus Vi. So think about the square and the triangles. I'm just redoing the same kind of idea here. Now, it's not difficult to see that Ci intersection S is going to be just these the vertices. The vertices of Ci are actually V minus Vi, and so what I have then is that if I intersect all of these C1 through Cm, the intersection is empty, right? But if I intersect m minus one of them, any n minus one of them, the intersection is not empty. So I get exactly the definition of the Helly number, and so I must have that the Helly number of S is at least m. That's essentially the little argument that we had even already for the square. So okay, so that's a nice thing, and so we're going to basically rely on that lemma to try to prove the theorem. So just to prove the theorem, what we're actually going to do is we're going to run a little algorithm to construct our dual certificate. And it's very simple. I'm going to show you a little picture to illustrate how the construction works. So we're going to construct a sequence of sets, Q0, Q1, and so forth, until we reach our last one, which is going to be our dual certificate. So we start from Rn, the whole space. And as long as there is a point of S in the interior, what I'm going to do is I'm going to pick the one with smallest value of F. Let's say Tk is that value. And I'm going to essentially going to find a point Zk which has this value. And then I'm going to basically construct a half space through that point. There's a little technicality that comes into the picture. When I have ties, when I have several candidates, so several points are in the interior and they have the same value Tk, I have to be a little bit careful how I pick my next point Zk. And that's what this is all about. So maybe I'll just explain. So the point Zk that I want to pick is, I'm looking at this convex set Ck, which is the set where the function f is at most Tk, this value, the smallest value the smallest value of f of s for s in the interior of Q. k minus 1. So I look at this set, and if this set is smooth, there's no problem, but this set ck might not be smooth. It might have some faces. And if that set has some faces, then, let's use this notation. Fck of S denotes the smallest face of ck that contains point S. What I'm going to pick then, I'm going to pick the S such that the dimension of that face is largest possible. Okay, that's the one technicality. But okay, let's not worry about this for now. Let me show you a little example. So we start from R2, and we see that, okay, so this is the smallest value of the function for a point in S, 3. Okay, so, and there's no tie, so we just pick that and some subgradient. Well, here it's smooth, so we pick the gradient. And we're going to then look at this half space as our Q1. Okay, now in Q1, I'm now looking at the smallest values, and it's 4. And now I have a tie. Here it doesn't really matter because the function is smooth, and so the dimension of the face is 0 in each case, so there is no problem. So I just pick one of these 2 points, and then I define Q2 this way, right? So just do this recursively. But just for the sake of argument, let's assume that actually my C2 was not smooth down here, and it was kind of there was kind of a face of dimension 1 here in C2. Then here, I have to look at the smallest face that contains this point. Actually, it's still a face of dimension 0, the smallest face. So I would be justified in picking this. But let's assume somehow that my face of dimension 1 contains this point in its interior. Then I would have to choose this point instead of this one. Okay, so that's the algorithm. So okay, so then so C3 equals C2. Now I pick this half space intersected with the previous Q, and until I reach Q4, now I have no point of S in the interior. I'm done. That's going to be my final. That's going to be my dual certificate, basically. And let me make a couple of remarks. Iteration k of the algorithm can always be executed because, remember, here, we have to, we have to come up with a point that meets that value. But by the assumption that we made in the theorem, we know that basically this minimum exists, and so we can always perform the algorithm. And and so I don't know how much I want to get into the proof, but maybe I'll say a couple of things about the proof. So first, note that because we have this subgradient, the face of CK that contains ZK is really obtained this way. It's a CK intersected with this hyperplane. And so the proof has 3 steps to it. And the first one, in some sense, maybe is kind of is the key to the whole thing. We show that for every k, if we pick any 2 points, zi, zj, different, then we, in other words, only zi is on this face. The other zij's are not. They are strictly. So basically, what I'm saying is, claim 1 basically states that this property here holds. That so this property of strong optimality certificates, property 2, holds. And then once we have that, then we can show that if we look at z1 through zk, we have this nice property that V is in fact exactly the intersection of convex hull of V with the set S itself. And those are just the vertices of convex hull of S. So that's exactly what we wanted in our lemma. And then claim 3 is that essentially by applying the lemma, we're going to have that the algorithm stops after at most this many iterations. And when we finish, the set QK is actually S-free. And yeah, so should I spend a few minutes explaining this proof? Maybe I'll skip it. I think I'll skip it. So yeah, thank you very much.
All right, before I ask for questions, I'll just mention that because the talk is being filmed, the questions need to be recorded. So if you have a question, I'm going to have to bring the mic over to you. So with that in mind, does anyone have any questions?
So what if you took the max cut problem, perturbed the diagonal to make it concave?
Okay.
And then can you apply this to verify that you have some points that's, so you have a few points that you think might be optimal? Could you verify it, that you're optimal?
So yeah, I mean, that's a very good question. So I mean, actually, as I mentioned, our goal was actually to come up with a nice kind of primal dual algorithm, or at least try to find a way to construct this dual certificate sort of in a primal dual way. And unfortunately, we never managed to do this. And I think, I guess your question about max cut is, is there kind of a clever way of coming up with some dual certificate, right? Unfortunately, I really don't have a good answer to that. Yeah, I mean, I think there's really a lot to be done when it comes to finding such certificates explicitly. I mean, we just showed that it exists, but of course, the way we constructed our algorithm, of course, immediately starts from the primal optimal solution, right? And then builds from there. So, I mean, of course, it's not what you want to do in practice. So, yeah. Yeah, I mean, the algorithm here is just to prove the theorem. It's definitely not meant to be a practical algorithm. But I think it'd be nice to be able to, what we were hoping, even in the plane, it'd be nice to have some nice kind of primal dual algorithm in 2D. How do you actually? Because I think the algorithms that exist right now are really more like primal type of algorithms, or dual algorithms maybe, but apparently, I don't know of any algorithm that goes back and forth between the primal and dual in this sort of discrete nonlinear case. But yeah, maybe the max cut problem is a good problem to start. Yeah.
It seems that another potential application of your result might be in proving that certain problems belong to the class, complexity class NP. For instance, you're looking at the problems of minimizing a convex function over potentially a discrete set.
Yeah.
And some of them are very complicated. It's not even clear that some of those problems are in NP a priori.
Yeah.
Even for the known cases, this might potentially lead to a shorter proof.
Yeah.
Because all you need is the existence and then putting some bounds on the size of the certificate.
Yeah, no, that's a great remark. That's a very, very good remark. And yeah, we've really not investigated this at all. But I think this is a great observation that might be able to prove NP results from this.
Are there any further questions? Okay, I have a quick question. Do you have a characterization of which sets have bounded or have finite Helly number?
No, I don't have. I don't know. I don't have a general answer. But yeah, as I said, there's the work of Aberkoff, who basically has investigated various special cases where you do have a finite Helly number. But yeah, I think this is also a nice open area, and just understanding better which sets have finite Helly numbers. Yeah, lots of good questions.
Okay, before I invite you to thank the speaker again, I'll just mention two things. The first is that there is a reception right now across the hall where there's going to be snacks and a cash bar. And the second thing is I'd like to present a small gift to the speaker to thank him for this wonderful talk. So can you please join me in thanking the speaker?